guys! Welcome to BSECE 33 channel. So meron na naman tayong panibagong lesson tungkol sa series parallel configuration. But before we proceed to the configurations, let us first talk about how diodes are used. In the early years of electronics, nearly all diodes were vacuum tubes. Today, most are made from semiconductors. Contemporary diodes can do almost everything that the old ones could, and also some things that people in the tube era could only dream about. So we will talk about 5 applications of how diodes are used. First, rectification. So kung mababasa naman ang meaning sa slide, so the constraint on this behavior are the forward breakover and avalanche voltages. Examine the circuit shown at A in figure 21. Suppose a 60 Hz AC sine wave is applied to the input. During half the cycle, the diode conducts, and during the other half, it doesn't. This cuts off half of every cycle, depending on which way the diode is lit up. Either the positive half or the negative half of the cycle will be removed. Mag-move on naman tayo sa drawing A, sa figure na nasa slide. Shows a graph of the output of the circuit at A. Remember that electronics flow from negative to positive against the arrow of the diode symbol. The circuit and wave diagram of the figure shows a half-wave rectifier circuit. This is the simplest possible rectifier. Number 2 is frequency multiplication. So often non-linearity is undesirable. The output wave from the diode looks much different than the input wave. The condition is known as non-linearity. Whenever there is non-linearity of any kind in a circuit, that is, whenever the output waveform is shaped differently from the input waveform, there are harmonics in the output. These are waves at integer multiplies of the input frequency. Non-linearity is introduced deliberately to produce frequency multiplications. So, ang diodes ay ideal sa purpose na ganito. So, isang simple frequency multiplier circuit ay makikita sa slide. So, the output LC circuit is tuned to the desirable and harmonic frequency. So, for a diode na mag-work as a frequency multiplier, it must be a type that would also work well as a detector at the same frequencies. This means that the component should act like a rectifier, hindi bilang capacitor. Next is signal mixing. Suppose there are two signals with frequencies F1 and F2. F2 bilang higher frequency and F1 yung wave with the lower frequency. If these two signals are combined in a nonlinear circuit, new waves result. Yung isa ay may frequency na F2 plus F1 at yung isa naman ay may frequency of F2 minus F1. These sum and different frequencies are known as bit frequencies. The signal themselves are called mixing products or heterodynes. Fourth is switching. One type of diode made for use as an RF switch has a special semiconductor layer sandwiched in between the P-type and N-type material. The material in this layer is called an intrinsic semiconductor. Ang isang intrinsic semiconductor ay nagre-reduce ng capacitance of the diode so that it can work at higher frequencies than an ordinary diode. A diode with an I-type semiconductor layer sandwiched in P-type P and N-type layers is called a PIN diode. Lastly, panglima, voltage regulation. Most diodes have an avalanche breakdown voltage that is much higher than the reverse bias ever gets. The value of the avalanche voltage depends on how a diode is manufactured. Zener diodes are specially made so they exhibit well-defined constant voltages. Suppose yung Zener diode natin ay may avalanche voltage of 50 volts. If reverse bias is applied to the PN junction, the diode acts as an open circuit as long as the bias is less than 50 volts. Magkakaroon naman ng reverse bias voltage kapag na-reach niya yung 50 volts, even for a brief instance of time. The diode conducts. This effectively prevents the reverse bias voltage from exceeding 50 volts. After discussing the different applications of diodes, let us now talk about load line analysis using piecewise linear equivalent model. So the straight line is called the load line because the intersection on the vertical axis is defined by the applied load R. So tignan natin yung picture. The effect of the pressure established by the DC is to establish a conventional current in the direction indicated by the clockwise arrow. The fact that the direction of this current has the same direction as the arrow in the diode symbol reveals that the diode is in the on state and will conduct a high level of current. A straight line drawn between the 2 points will define the load line as depicted sa figure. Change the level of R, the load, and the intersections on the vertical axis will change. The result will be a change in the slope of the load line and a different point of intersection between the load line and the device characteristics. So take note of the formulas written sa slide dahil magagamit natin ito sa mga susunod na topic. So, we know that voltage or E is equals to VD plus IDR. And meanwhile, ID is equals to E over R, and then VD is equals to E over ID is equals to 0 ampere. So magagamit natin lahat ng formulas ito sa susunod na slides. So meron tayo ditong sample of load line analysis. For the series diode configuration of figure 2.3a employing the diode characteristics of figure 2.3b, determine A, VDQ and IDQ, and B, VR. So makikita natin dito sa circuit na merong voltage of 10 volts, may silicon, and may resistor na 0.5 kilo ohm or 500 ohms. So first, kukunin muna natin yung ID. We know that ID is equals to E over R. So, 10 volts over 0.5 kilo ohms ay magkakaroon tayo ng 20 milliamperes. So, gumamit na lamang kayo ng scientific calculator. So, the resulting load line appears sa figure 2.4a. So, yung intersection between the load line and the characteristics curve defines Q point as yung VDQ natin is equal to 0.78 volts and IDQ natin is 18.5 milliamperes. So, in-estimate na lamang natin ito. Not equal, pero almost equal. So, VR now is equals to E minus VD is equals to 10 volts minus 0.78 volts. Yung VDQ natin kanina ay magkakaroon na tayo ngayon ng VR of 9.22 volts. So, ang resistor voltage natin is 9.22 volts. Another solution sa example natin kanina ay una, kukunin muna natin yung RD. Para makuha natin yung RD, VDQ is over IDQ is equals to RD. So, RD is equals now to 0.78 volts over 18.5 milliamperes. Pag kinalculate natin, magiging 42.16 ohms. So, now, kukunin naman natin yung current, which is ID. Take note that ID is equals to E over RD plus R. So, E over RD plus R is equals to 10 volts over 42.16 plus 500 ohms is equals to 10 volts over 542.16 ohms. Kapag kinalculate natin, makukuha natin yung 80.5 milliamperes. And now, para makuha natin yung VR or yung resistor voltage, RE over RD plus R is equals now to 500 ohms times 10 volts over 42.16 ohm plus 500 ohm is equals to 9.22 volts. So makikita natin na kahit ano sa dalawa ang gamitin nating solution, magkikame up pa rin tayo sa resistor voltage na 9.22 volts kasi same lang naman yung circuit na ginamit natin. The last slides, we found that the results obtained using the approximate piecewise linear equivalent model were quite close, if not equal, to the response obtained using the full characteristics. In fact, if one considers all the variations possible due to tolerance, temperature, and so on, one could certainly consider one solution to be as accurate as the other. So now let us move on to the series diode configurations. So the forward resistance of the diode is usually so small compared to the other series elements of the network that it can be ignored. For the conduction region, the only difference between the silicon diode and the ideal diode is the vertical shift in the characteristics, which is accounted for the equivalent model by a DC supply of 0.7 volts, opposing the direction of forward current through the device. So kapag ang voltage ay less than 0.7 volts para sa isang silicon diode and 0 volts para naman sa ideal diode, yung resistance ay sobrang taas compared sa ibang elements ng network that its equivalent is the open circuit. So generally, ang diode is in the on state if the current established by the applied source is such that its direction matches of the arrow in the diode symbol. For instance, mentally replace the diodes with resistive elements and note the resulting current direction as established by the applied voltages. If the resulting direction is a match with the arrow in the diode symbol, conduction through the diode will occur and the device is in the on state. So, lagi nating iisipin na magkakaroon lamang ng conduction sa diode kapag ito ay nasa on state. So, makikita natin sa slide na ang silicon ay merong 0.7 volts at ang ideal naman ay merong 7 volts. So, tignan natin ito sa approximate and ideal semiconductor diode models. Ngayon, let us take note yung mga formula na naman na gagamitin, which is VD is equals to VK, VR is equals to E minus VK, and ID is equals to IR is equals to VR over R. In figure 2.10, the diode of figure 2.7 has been reversed, mentally replacing the diode with a resistive element as shown in figure 2.11 will reveal that the resulting current direction does not match the arrow in the diode symbol. The diode ay nasa off state, resulting sa equivalent circuit of figure 2.12. Dahil sa open circuit, yung diode ay magkakaroon ng 0 ampere and yung voltage across resistor ay 0 volts. Why? Because VR is equals to IR times R or is equals to ID times R, which ID is equals to 0 ampere, therefore voltage of the resistor is 0 volts. Meron tayong example dito. For the series diode configuration of figure 2.13, determine VD, VR, and ID. So makikita natin sa circuit na merong voltage of 8 volts. Ito yung source voltage natin. Meron tayong silicon and resistor na 2.2 kilo ohms sa circuit. Now, kunin na natin yung diode voltage. We all know that the diode voltage of silicon is 0.7 volts. Kunin naman natin yung resistor voltage. Para makuha ito, pagmaminusin lamang natin yung source voltage at yung voltage ng diode. So, 8 volts minus 0.7 volts is equal now to 7.3 volts. So, now, kunin na natin yung ID. ID ay equal lamang sa IR dahil nasa series circuit lamang sila. We all know that sa series circuit, constant ang current. So, now, ID is equal to IR is equal to VR over R. So, para makuha natin yun, 7.3 volts over 2.2 kilo ohm ay approximately equal to 3.32 milliamps. So, meron na naman tayong panibagong example. Determine I, V1, V2, and VO for the series DC configuration of figure 2.25. So, makikita natin sa circuit na meron tayong dalawang source voltage, meron tayong dalawang resistor, meron tayong silicon, at meron tayong isang voltage output. So, first, kunin muna natin yung current ng circuit. So, I is equals to E1 plus E2 minus VD over R1 plus R2. Equivalent ito sa 10 volts plus 5 volts minus 0.7 volts over 4.7 kilo ohms plus 2.2 kilo ohms ay equal lamang sa 14.3 volts over 6.9 kilo ohms is equals to I is approximately equal to 2.07 milliamperes. Now, kunin naman natin yung V1. V1 ay IR1 lang. So, 2.07 milliampere times 4.7 kilo ohm ay equal sa 9.73 volts. V2 ay IR2 is equals to 2.07 milliampere times 2.2 kilo ohm is equals to 4.55 volts. So, nakuha na natin yung current V1, V2. Kukunin naman natin yung output voltage. Para makuha yung output voltage, V2 minus E2 lamang siya, which is equal to 4.55 volts minus 5 volts is equals to VO or output voltage now is negative 0.45 volts. Now, paano natin nakuha yung VO? Maggagamit lamang tayo ng Kirchhoff's voltage law sa output section. The methods applied in series configurations can be extended to the analysis of parallel and series parallel configurations. For each area of application, simply match the sequential series of steps applied to series diode configurations. So,
So, an example of a parallel diode configuration ay makikita natin sa example 2.10. So, determine yung VO, I, ID, and ID2. So, now, unahin muna natin kunin yung VO, which is we know that it is 0.7 volts. So, para naman makuha natin yung current, I1 is equals to VR over R. So, VR over R is equal rin siya sa E minus VD over R is equals to 10 volts minus 0.7 volts over 0.33 kilo ohms ay I1 is equal now to 28.18 milliamps. So now, kukunin naman natin yung ID1. Ang ID1 at ID2 ay equal lamang since parallel naman sila. So, ID1 over ID2 is equals to I1 over 2. Now, is equals to 28.18 milliampere over 2 is equals to 14.09 milliampere. So, makikita natin dito, parang hinati lamang yung current na dumadaloy since una, I1, papasok siya sa resistor and now nahati siya sa dalawa because of the two diode silicons. If the green diode were to be replaced by a blue diode, the problems would develop as shown in figure 2.32. Recall natin na yung forward bias required to turn on a blue diode is about 5 volts. The result would appear to require smaller resistor R to establish the current of 20 milliampere. However, note din natin that the reverse bias voltage of the red LED is 5 volts din, but the reverse breakdown voltage nito ay only 3 volts. The result is the voltage across the red LED would lock in at 3 volts as shown in figure 2.33. The voltage across R would be 5 volts and the current limited to 20 milliampere with a 250 resistor but neither LED would be on. A simple solution sa problem natin na nauna ko na nasabi is to add the appropriate resistance level in series with each diode to establish the desired 20 milliampere and to include another diode to add to the reverse bias total reverse breakdown voltage rating, as shown na makikita natin sa figure 2.34. When the blue LED is on, the diode in series with the blue LED will also be on, causing a total voltage drop na 5.7 volts across the two series diodes and mayroong voltage na 2.3 volts across sa resistor 1, establishing a high emission current of 19.17 milliampere. At the same time naman, yung red LED diode natin and its series diode will also be reverse biased. But now, the standard diode with a reverse breakdown voltage of 20 volts will prevent the full reverse bias voltage of 8 volts from appearing across the red LED. When forward biased, the resistor R2 will establish a current of 19.63 milliamperes to ensure a high level of intensity for the red LED. So, an example of a series parallel configuration ay makikita natin sa example 2.12, which would determine the voltage VA for the network of figure 2.35. Initially, it might appear that the applied voltage will both turn the diodes on because the applied voltage is trying to establish a conventional current through each diode that would suggest the on state. Now, the resulting action can be explained by remembering that there is a period of buildup of the supply voltage from 0 volts to 12 volts, even though it may take milliseconds or microseconds. Now, yung instant increasing supply voltage reaches 0.7 volts, yung silicon diode natin ay mag-on and maintain niya yung level of 0.7 since the characteristics is vertical at this voltage. Now, yung current ng silicon diode will simply rise to the defined level. Yung result ng voltage across sa green LED will never rise above 0.7 and will remain in the equivalent open circuit na makikita natin sa figure 2.36. So, output voltage now is 12 volts minus 0.7 volts ay equal sa 11.3 volts. So, last example, determine the currents I1, I2, and ID2 for the network of figure 2.37. So, makukuha na natin yung I1 since given na yung voltage ng diode 2 and yung R1 natin. So, VK2 over R1 is equals to 0.7 over 3.3 kilo ohms is equals to 0.212 milliampere. Para makuha natin yung voltage, ay i-apply natin yung Kirchhoff's voltage law. So, now, negative V2 plus E minus VK1 minus VK2 is equals to 0. So, ililipat natin yung V2 sa kabila. V2 now is equals to E minus VK1 minus VK2 is equals to 20 volts minus 0.7 volts minus 0.7 volts is equals to 18.6 volts. Para makuha natin yung I2, equal lamang siya sa V2 over R2. So, 18.6 volts over 5.6 kilo ohms ay magkakaroon ng 3.32 milliampere. So, para makuha naman na natin yung ID2, I2 minus I1 lang siya. So, I2 minus I1 is equals to 3.32 milliampere minus 0.12 0.212 milliampere ay magkakaroon tayo ng ID2 of 3.11 milliampere. So, yun lamang para sa topic na series parallel configurations. I hope na marami kayong natutunan. So, for more questions, just comment down below. Thank you!